Our senses define our reality. Among our 5 primary senses, touch has always held a special distinction. Sight, hearing, smell, and taste are distal senses. You don't need to make contact to perceive them. But touch, by its very definition, is a proximal sense. It requires physical contact. But what if that fundamental assumption isn't entirely correct? What if our sense of touch has a distal component we never realized? A new study from Queen Mary University of London and University College London suggests exactly that. Humans possess the ability to feel the presence of objects just before making physical contact. This ability, remote touch, first captured scientists' attention in the animal kingdom, and nature is full of masters of this sense. One of the most striking examples is the crocodile. If you look closely at a crocodile's head, you'll see small, dark specks around its jaw, almost like a beard shadow. These are thousands of sensitive pressure detectors called issos, integumentary sensory organs. The crocodile lies in wait, its jaw resting on the water's surface. When prey in its vicinity creates even a microscopic ripple, that pressure wave propagates across the water. The thousands of sensors on the crocodile's jaw detect the microsecond time delay, between when the wave hits each sensor. Using this timing difference, its brain instantly performs a triangulation, calculating the prey's exact location with extraordinary precision. The true genius of this system is that it overcomes the physics of light refraction. Even if the crocodile's eyes see the prey in the wrong location, due to light bending at the water's surface, it trusts the flawless tactile information from its jaw, striking its target with near-perfect accuracy. The other masters focused on by this research are shorebirds. The paper highlights birds like the sandpiper. Their method is slightly different and even more sophisticated. The problem? The bird needs to find a small shellfish buried under sand it cannot see or smell. The tool? Its long, thin beak. The secret weapon? The very tip of its beak is filled with thousands of microscopic pressure sensors embedded in the bone and tissue called Herbst corpuscles. These can detect hundreds of vibrations per second. How it works? The bird repeatedly taps its beak into wet sand. This isn't random pecking, it's a systematic probe. Wet sand is the perfect medium because the incompressible nature of the water between the grains transmits pressure waves rapidly, unlike dry sand, which dampens them. Each tap sends a small pressure wave, those ping-ping ripples, into the sand. If that wave just hits more sand, the energy dissipates and no signal returns. But if that wave strikes a hard object, a shellfish or a crab, it reflects off that object, just like sound echoing off a wall. This returning mechanical echo, the reflected pressure wave, is then detected by the thousands of Herbst corpuscles in the beak tip. The bird's brain, much like the crocodile's, calculates the intensity and microsecond delays of this returning signal. It performs its own triangulation and knows the exact depth and direction of the prey. The result? The bird never physically touched the prey. It touched the echo of a pressure wave it sent out. This is, quite literally, a biological sonar. We call this active sensing because the bird itself creates the signal. So what about us? The human experiment reveals how our ability works. Our method isn't sonar, it's more like resistance mapping. The problem? You must find a hidden cube buried in a box of sand, blindfolded. You are only allowed to sense its location, not touch the cube itself. The tool? Our fingertips. The secret weapon? The dense pressure sensors or mechanoreceptors in our fingertips. And this is the key. Our brain's proprioception, the body's sixth sense for knowing where its parts are in space and what they should be feeling. How it works? You gently move your finger through the sand. As your finger moves, it pushes the sand in front of it, creating a small pressure field. According to the principles of granular physics, when a slow force is applied, the sand grains behave like a dense fluid, flowing around your finger. This flow creates a consistent, expected level of resistance. Your brain, through neural adaptation, codes this feeling as normal within half a second and filters it out. But as your finger gets close, perhaps 2 or 3 centimeters to the hidden cube, that pressure field in front of your finger hits the cube. The cube is solid. It doesn't flow like sand. The sand grains get jammed in the small space between your finger and the cube. This jammed sand causes a sudden spike in the resistance your finger feels. This is the aha moment. Your brain, using proprioception, says, wait, I am suddenly having to apply more force to maintain the same speed. This is not normal. There must be an obstacle. The result? You never touch the cube. You touch the extra resistance created by the jammed sand, which was caused by the cube's presence. In summary, the bird asks, is anything out there, by sending a signal, a pressure wave, and listens for the yes, I'm here echo. That's active sonar. The human asks, is everything normal while moving, and feels the environment, the sand, scream, no, roadblock ahead. That's resistance mapping. Both are based on the same principle, detecting an object's disturbance in a medium without direct contact. And this is where the study's most striking point emerges, the human versus robot comparison. A robotic arm with tactile sensors was trained with an LSTM artificial intelligence algorithm. In theory, the robot could sense objects from further away than the human. However, its overall accuracy was only 40%. The human accuracy was 70.7%. Why did the more sensitive robot fail? The answer: false positives. The robot reported every random change in pressure, every bit of noise in the sand as an object. It was processing raw data. The human brain, on the other hand, acted as a perfect biological noise filter. Because of that secret weapon, proprioception, our brain wasn't just processing passive touch data, it was comparing that data against the context of our arm's speed and our muscle tension. It could instantly tell the difference between random noise and a real resistance spike caused by a real object. In short, the robot processed data. The human processed meaning. This discovery has profound implications for technology. 1. Archaeology. A remote touch sensor on a robot could map the precise shape of a fragile buried artifact without touching it, simply by feeling the resistance changes in the soil around it. 2. Medicine. Think of a surgeon performing palpation, feeling for tumors. Robotic tools based on this principle could detect hard masses deep inside an organ not by cutting, but by feeling the mechanical echoes they send through the soft tissue, elastography. 3. Space exploration. NASA's InSight mole on Mars failed when it hit unexpected rocks. A remote touch probe could detect such obstacles before hitting them, finding the clearest path underground. And 4. Virtual reality or VR and haptics. Today's VR gloves vibrate when you hit a virtual wall. This research promises something new, a glove that applies subtle, increasing resistance as you approach the wall, mimicking that pressure field. It would transform touch from a simple contact sense into a perceivable field. In the end, this study doesn't just reveal a hidden human ability. It proves that the human brain, with its integrated sense of self, remains a far more sophisticated noise filter than even our most advanced artificial intelligence.